Transformations of logarithmic functions. In this video, we're going to take a closer look at the characteristics that change the shape and the size of a logarithmic function. Let's take a look using these examples. We're going to graph the function log x minus 2 minus 5. We will state the key features of the function: the domain and range, the x-intercept if it exists, the y-intercept if it exists, and the equation of asymptote. So we'll start with number 1. Graph the function y equals log x minus 2 minus 5 and state its key functions. So here's the graph that we will get. The graph in green is your original graph of y equals log x. The graph in aqua is the graph for y equals log x minus 2. And you will see that to get this graph, we shift 2 units to the right, which makes the horizontal translation. Then we graph y equals log x minus 2 minus 5, and we see now that we have a shift down by 5, which is your vertical translation. So what is our domain? Well, our domain is the set of x such that x is greater than 2, and the range can be any real values. The x-intercept, where the line crosses the x-axis, which we will not see, but we know we can calculate it by substituting y equal to 0. It will occur at the number 100,002. Now you know why we can't see it. The x-intercept, if there is one, should occur when x is equal to 0. But when we substitute x equal to 0 into our log equation, we find that we get log negative 2, which is undefined. This means that there is no y-intercept. The vertical asymptote will occur when x minus 2 is equal to 0, which is when x is equal to 2. Now we want to take a look at another problem. Sketch a graph of each function, y equals 5 log x plus 3, and then y equals log negative 2x plus 4, and identify the key features for each function. Here's a tip. When you're applying multiple transformations and translations, which we will be doing, it can be helpful to focus on certain points and see what their behavior becomes, such as, for example, 1 and 0 and 10 and 1. Make sure to also note the position of the asymptote as it changes. Let's begin. So here we have the graph y equals log x plus 3. So we start out by drawing the graph for log x, which is in green, and then we add 5, and so we see our vertical shift upward. We'll check our anchor points. So 1, 0 becomes, oh, it's still 1, 0, and 10, 1 becomes 10, 5. The asymptote then, for now, will still be x equal to 0. Now apply the horizontal shift of plus 3, shown now in the blue. So what has happened The anchor points and the vertical points and the vertical asymptote have all shifted 3 units to the left. So 1, 0 has become negative 2, 0, and 10, 5 becomes 7, 5. Sketch a graph of this function. Y equals log negative 2x plus 4. But before we begin, let's do an analysis to see if we're right. So the negative is going to be a horizontal reflection in the y-axis. The 2 represents a horizontal compression by a factor of 1/2. The plus 4 represents a translation up 4 units. Let's see if we're right. We'll start with the 2x. Remember that our aqua is the original with our anchor points of 1, 0 and 10, 1. And then our horizontal shift becomes 0.5 and 2 and 5 and 1, shown on our green. For now, the asymptote is still at x equal to 0 in this step. Now we'll do the reflection, which is the negative 2. So we will reflect around the y-axis, and our anchor points will change from 0, 5, 0 to negative 0.52. 5, 1 will be reflected to negative 5, 1. Now we're going to apply the vertical translation, plus 4. So our point 0.50 becomes negative 0.54. Negative 5, 1 becomes negative 5, 5. The asymptote remains unchanged. Sample problem number 2, part B. For the function y equals 5 log x plus 3 as shown in the diagram, the domain is x is an element of the real numbers and x is greater than negative 3. The range, x is an element of the real numbers. The x-intercept occurs when y is equal to 0. How do we know this? Y is equal to 5 log x plus 3. 0 is 5 log x plus 3. 10 to the 0 is x plus 3. 1 equals x plus 3, so x must be negative 2. The x-intercept is negative 2. How do we know this? The y-intercept occurs when x is equal to 0. So we know that we'll substitute in x as 0, and we will solve for y and get 2.386. There is a vertical asymptote at x is equal to negative 3. Next question. For the function y equals log negative 2x plus 4, what are the characteristics? The domain is an element of the real numbers, and x is less than 0. The range, y is an element of the real numbers. Since the y-intercept occurs when y is equal to 0, substitute in 0 for y, and you will get the answer, x equal negative 0.00005. The y-intercept occurs when x is equal to 0. So y is equal to log 0 plus 4. Because log 0 is undefined, there is no y-intercept. The vertical asymptote is x is equal to 0. So, in summary, if you have y equals log x plus c, it translates up c units if c is greater than 0, down c units if c is less than 0. If you have log of x minus d, it translates d units if d is greater than 0, translates left d units if d is less than 0. Y equals a log x stretches vertically by a factor of a if a is greater than 1, and by a factor of a if a is less than 1, meaning the absolute value. The reflection is in the x-axis if a is less than 0. Y is log kx compresses horizontally by a factor of 1 over k. If k is greater than 1, 1 over k, if k is less than 1, which of course is your absolute value. Reflection in the y-axis if k is less than 0. To perform multiple transformations, make sure you have the right form of the equation as given. Apply the horizontal, vertical stretches or compressions first, then apply your reflections, and then apply your translations. Tricky stuff, but I'm sure we're up for the task.